Hi everyone. Thanks for your patience. I'm Don Barry. I'm a professor of geology here at Mesa College, and I help coordinate the STEM lecture series. We are glad you're here tonight, and we got through our technical difficulties. So it gives me great pleasure to introduce tonight's speaker, Professor Danica Moore. She is a true San Diego native. She was born and bred and raised in San Diego, and she was a Mesa College student. And from Mesa College, she went on to UCSD, where she got her Bachelor of Science, and then from there, the University of Oregon, where she got her Master's of Science, specializing in undergraduate curriculum and also physical chemistry. So please give a warm virtual welcome to Professor Danica Moore.
Yay! Awesome. All right. Well, I apologize in advance because I'm a little bit nervous. It seems like I probably shouldn't be because this is what I do for a living. But anytime I give a new talk or something that I'm not as familiar with, I'm a little out of sorts. So I just wanted to let everybody know that if you have any questions or if you're unclear on something that I'm talking about, I would love you to just stop me and ask a question. So I'm happy to field questions as we go. I know that's maybe not quite as traditional, but it makes me a little more comfortable. So yeah, so the title of the talk is Caesar's Last Breath, an Atmospheric Tale. So where did I come up with this crazy name? So there's one of my favorite science authors, name is Sam Keen. This is a link to his website, so please, if you want to dig deeper, I encourage you to do so. He's written a number of popular science books. My favorite is this one, but in addition to this, The Disappearing Spoon is a really, really fascinating tale of the history behind the periodic table. I know I just sold that really well, and you guys are like, that's great. History of the periodic table sounds fascinating, but it actually is. It's really, really well written, very accessible. So I swear he's not paying me, but that's where I got the idea for this talk. So that's Sam Keen, Caesar's Last Breath. So the idea that he introduces in this book, Caesar's Last Breath, is a concept that's not particularly new. But it's the idea of, are we breathing the same air molecules as Julius Caesar's last breath? So this is one of those pinnacle moments in literature and in history, right? Julius Caesar taking his last dying breath, and all of the air escapes from his lungs. So I don't know about you, but when I heard this, I was like, that's super gross. I'm definitely grossed out by the idea of breathing air that belonged to somebody who is long since dead. But so if you thought that was well, then you're in good company. But what was I going to say? Excuse me. But the concept is not particularly novel, right? The idea that we share air, right? I think we're better at thinking about the fact that we share our biological stuff, right? Our skin and bones, the things that we're made of. Circle of lifestyle, that's where this is coming from, if you were wondering about that picture earlier. Right, so I think we're more comfortable with that idea, but the idea of how we're connected through the air is a little more nebulous, right? It's a little bit less instinctive, and the air is invisible. It's not particularly tangible. So I want to kind of explore this idea and take you guys on that exploration with me. So as I've read this book several times now, and in this last go around was my first time reading it since the pandemic, and I had a whole kind of set of new thoughts about this, because our relationship to the air, I feel like, has fundamentally changed. Do you guys feel that way as well? Especially during the pandemic times, I feel like we became kind of afraid of sharing air, right? So I thought this idea of shared air is especially interesting in light of that. So anyways, just a little aside from off the top of my brain. So back to the idea of Caesar's last breath. So So we can actually quantify this. I promise I'm not going to make you do any math. And for the chemists in the room, there won't be any sig figs involved, so I apologize. But at any given time, our lungs contain about 1 to 2 liters of air, right? 1 mole of air has 6.022 times 10 to the 23rd molecules of air. That's a lot of freaking air, right? So based on our current, just to give you some scale for that, based on our current estimation of how many stars there are in the universe, we have about 1/10 of a mole of stars in the universe, right? So that's a really, 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 really big number. And the density, the relative density of gas in the atmosphere is such that there's about 22.4 liters per 1 mole of gas, right? So 1 mole, all of those 6.022 times 10 to the 23rd molecules, right, would occupy 22.4 liters, right? So if a breath is about 1 to 2 liters of air, that means that one's dying breath, whether we're talking about Caesar or otherwise, would be about 5.4 times 10 to the 22nd molecules of air. So just to try and get this number across to you, 54 million billion molecules, right? That's a lot of molecules. The air from Caesar's last breath will have cycled around the planet many times. On average, a low reactive molecule takes about a year to travel around the planet, so we've had plenty of those in between Caesar's dying and now. So convection, natural dispersion, all of that is going to disperse these gases all around. So assuming they're distributed completely evenly throughout the atmosphere, and the atmosphere, this is a very rough calculation, the atmosphere is about 7 times 10 to the 22 liters. That's our atmosphere, our little thin blankie on our Earth. So if you do the math on that, this big old number divided by this big old number, and you get about 1 molecule in every breath, right? So on average, about every single breath we take, we are probably inhaling 1 molecule from Caesar's last breath. And that's obviously not unique to Caesar, right? That's anybody that we encounter, right? We are all constantly sharing air, whether we like it or not. But I found that to be just a phenomenal, mind-blowing thing, right? We absolutely share air throughout time and space. We've been sharing air. So now I want to get into what is air, right? So how many of you have taken chemistry before? Don't answer, Donna. One of you. Okay, cool. So I think when I teach students, a lot of students are not aware of the fact that the majority of our atmosphere is actually not oxygen, right? So we need the oxygen to breathe, but it's actually it's a big component, but it's not the biggest, right? Nitrogen is the biggest component. So, and that's good news for us because nitrogen is a relatively inert gas, and we'll talk all about that in just a second. So this is my own little picture of if you zoomed in on the air, the vast majority of air would be nitrogen, a little bit of oxygen, and then all these other little gases are just a tiny smidgen of a fraction, right? So we have a decent amount, almost 1% of argon. We have a little bit of carbon dioxide, and then the rest is just trace gases, right? So it may seem like oxygen and nitrogen are the most important or exciting part of the atmosphere, but you would actually be wrong. So thinking about a glass of wine, how many of you guys are old enough to drink? I think all of you, hopefully. All right, so hopefully you've enjoyed a glass of wine before, right? The 2 major components in a glass of wine are alcohol and water, right? But that's not what makes a wine taste amazing or terrible, right? It's all of the little other things that are in the wine that really give it the character. So that's what I want to kind of explore. We'll talk about the big guys, the small, big makeup, and then we'll talk about some of the little ways that we change the atmosphere. So the air that we breathe is very different now than at the beginning of the Earth's history. So early on in Earth's history, the atmosphere, if you could call it that, was 95% carbon dioxide. So carbon dioxide, definitely not conducive to most living things, at least as we know them. The other cool effect of having an atmosphere made of 95% carbon dioxide is carbon dioxide is a greenhouse gas, right? Is everybody familiar with greenhouse gases? You've heard this term before? Yeah? So the temperature, the average surface temperature with that amount of carbon dioxide would be about 400 degrees Celsius. No big deal, just a cool 400 degrees Celsius, 4 times the boiling point of water, as opposed to the average surface temperature now, which is a balmy 20 degrees, right? So big difference in the atmosphere, and we'll talk about what led to those changes. So just to give you a little bit of information on what the atmosphere looks like, there are these beautiful pictures that diagram the different layers of the atmosphere. The one that we interact with most is the troposphere. We'll talk a little bit about the stratosphere, that next level up. But all of the upper levels of the atmosphere are pretty much empty space. The vast majority of air is in that first 30 or so miles of atmosphere. And as a science person, I have to point out that I hate this picture. This picture. Do you guys know why? What does it look like? That Earth is the tiniest little Earth that I've ever seen in my life, and the atmosphere is absolutely gigantic. The relative scale is horrifying here, right? The actual relative scale of the atmosphere is literally just this little ghost of blue across the top, right? So the radius of our planet is about 3,600 miles, and the atmosphere, the total atmosphere, extends another 100 beyond that. And the parts that we're going to talk about, the parts that contain most of the mass, are just 30 miles, right? So literally here to East County, right? It's not very far. So it's a very, very small little piece of our planet. So yes, we're very happy that we have some carbon dioxide in our atmosphere. We need at least a little bit of it, because if we didn't, then our temperature, the average temperature of our planet would be negative 18 degrees Celsius. Pretty chilly, not very inviting. All right, so in order to get into these gases a little bit, I hope I'm not traumatizing anybody. I'm always aware of that. I wanted to talk a little bit about Lewis structures. So the way that we represent molecules in chemistry is we talk about shared electrons between atoms in a molecule. So the way that we represent those shared electrons is we use a little line that represents 2 shared electrons, right? So a line is 1 shared pair. Little dots next to an atom indicate an unshared pair, or a lone pair. And sometimes you can have 2 lines or even 3 lines connecting atoms. That would be a double or a triple bond, right? So in that case, you would have, for a double bond, you're sharing 2 sets of electrons, so 4 total. Triple bond, you got 6 electrons. So, getting into nitrogen. So nitrogen, as you can see, is a diatomic element. So most elements on our periodic table exist by themselves, but nitrogen is not one of those. It's diatomic, it's codependent, it likes hanging out with its other nitrogen buddy. It likes hanging out with its other nitrogen buddies so much so that it is really hard to get nitrogen atoms to separate from each other, right? Which is a good thing because it makes nitrogen, again, relatively inactive, which is good for us because we breathe in a lot of nitrogen every time we breathe, and if it was highly reactive, that would be problematic for us. So another fun fact about nitrogen gas, it's what gives the nitro in beer and coffee the kind of velvety texture because it's a very small gas. Nitrogen was originally discovered in 1772 by Daniel Rutherford. There were actually a bunch of people that did work on the atmosphere that were all working on it at the same time. So it's kind of arguable who made which discovery, but that's what the history books tell us. So nitrogen discovery, and then 120 years later, after 130 years later-ish, one of the big problems in the early 19th century, the early 20th century? 1900s, let's do that. The early 1900s was there wasn't enough food to feed the population. So we had population growth up to a certain point, but at some point we lacked the amount of fertilizer to grow food for an ever-growing population. So these two guys, really fun-looking guys, Fritz Haber and Karl Bosch, figured out a way to react nitrogen with hydrogen gas and form ammonia, which is a precursor to fertilizer. So this was the very first time that we were able to do this reaction. Even though our atmosphere is 80% nitrogen, right, we have a really hard time accessing it because of that triple bond, right? So we need to get nitrogen by itself in order to make it bioavailable to plants, right? So, if anybody knows a little bit about energy and entropy, I'm going to give you the quick and dirty on this. But if you have negative energy, that means that this reaction is happy energetically, right? But entropy, which is a measure of disorder, has one molecule plus 3 molecules, 4 molecules, becoming 2, right? So that's taking a bunch of disorganized molecules and making them into less molecules. That's not happy. That's sad face. And that's another big reason why this reaction was so hard to get going. So the way that they figured a way around this was by using what's called a catalyst. Has anybody heard of a catalyst before? Yeah? So catalysts are things that are able to make a reaction go faster, right, without actually being used up in the reaction. They tend to be metals. The first one that Fritz Haber came across was osmium. I don't know a lot about osmium. That's kind of my only fun fact about it. But Karl Bosch's big part in this process was that he was able to scale up the process. So the process that Fritz Haber had designed, and this is true of a lot of things in chemistry, you get a reaction to work in the lab, it's great, fantastic, but if you really want it to be industrialized, you have to scale up the process, right? And so scalability is a big issue in going from point A to point B with production of chemicals. So that was really Karl Bosch's contribution. He figured out how to catalyze this reaction with a mixture of iron and some other metals that was way cheaper and was able to scale up a lot better. So these guys are single-handedly responsible for feeding about half of the world's population. Half of the world's population would not be alive today if it weren't for these guys, okay? Are you ready for the twist? Yeah? You're like, okay, whatever.
Go for it. Go for it.
So, the twist, oh, I got a question. Platinum is considered a catalyst. We'll talk about that actually later on in the talk if we make it that far. So I'm going at a snail's pace, but yes, we will talk a little bit more about platinum as a catalyst. So the twist in this story is that Fritz Haber was a Jewish man in Germany. Karl Bosch was the same. And both of them were a part of the movement in the early stages of World War I to really prop up the German military. So Fritz Haber is actually the father of chemical warfare. So he thought, all this work that I've done on gases is great. How can we weaponize this for Mother Germany, right? So he was responsible for inventing the use of chlorine gas as warfare. So chlorine gas, if you don't know a lot about it, another diatomic molecule. It is very angry, and when you inhale it, it's a gas. When you inhale it, your lungs become so irritated that you basically drown in your own lung fluid. So it's like drowning on dry land. It is a horrible way to die. So not a great pitch for this guy, right? There's definitely some other stuff going on. So Fritz Haber's involvement in World War I kind of saved him from some of the things that came along with the Nazis in World War II. But pretty sad story for this guy. His wife killed herself, his son killed himself, and he was not very politely asked to leave Germany because he was only allowed to stay for so long until it became get everybody out that is of Jewish heritage. Some of his early work on pesticides, one of them you might recognize, Zyklon A, was actually used in World War II to make Zyklon B, which was what they used to gas the Jews in concentration camps. So really, really rough story, this guy, Fritz Haber, right? He single-handedly helped feed half of the world's population and was also responsible for the deaths of millions of people in horrific ways to die. So really tale of two worlds in terms of how science can work in the hands of different people. So on to oxygen. So oxygen was really found by a couple of different people. Joseph Priestley was the one that's credited with it, but Anton Lavoisier, actually, this is another hot topic of gossip. Anton Lavoisier technically stole the research of Joseph Priestley because they had talked about it over dinner, and Anton Lavoisier had the resources to be able to explore this research more than Joseph Priestley. So he was the one that ended up getting to name the gas, which was the right of whoever found an element, then you get to name it. So oxygen, as we saw at the beginning of the talk, was actually not a feature of our early atmosphere, right? So our early atmosphere was mostly carbon dioxide. So the thing that really changed our atmosphere was this, photosynthesis, right? And specifically the photosynthesis that came about from cyanobacteria, which are able to take carbon dioxide, which again, remember our atmosphere was rich in that, so it had plenty of food, carbon dioxide, water, and turn it into sugars and oxygen, right? So this process over time, obviously there was so much carbon dioxide that it was really easy to fuel this growth. And then beyond that, you had the evolution of more creatures that were able to do photosynthesis and so give us the atmosphere that we know today. Argon is one of the noble gases. So this guy, Lord Rayleigh, was a very meticulous and very boring chemist. He was one of the chemists that probably make people dread chemistry. He would sit up in his lab and do experiments over and over and over and over again because he wanted to get perfect results. And he poured everything that he had into cooling down the air and then separating the components of air. And what he found was every time he did this process of cooling down air and separating the components, he ended up with a 1% error. 1% every single time. And it was consistent, the error that he was getting. It didn't fluctuate. And past chemists had also seen this error, and 1% in those days with the equipment that they were working with, that was pretty reasonable. So a lot of his colleagues were like, yeah, you need to move on, friend. You need to stop doing that experiment. But yes, also true. So the error that was involved was so small that a lot of people just wrote it off, but he wasn't ready for that. He wanted to get this isolated and figure it out. The way that they isolated a lot of the elements in air was by reacting them, right? And he could not get this gas to react, right? So if you guys know, the noble gases are notoriously unreactive, right? They like to hang out by themselves. They don't want to do anything with anybody. So to me, the story of the discovery of argon is fascinating because it's shocking that we were ever able to figure out all of these noble gases, right? The amount of work that went into discovering all of these when there was no reaction to be done with them was truly painstaking. So argon was the first, and then very rapidly after that, Lord Rayleigh and William Ramsay were able to find more and more of these noble gases. They actually didn't introduce the idea of the noble gas or argon until they had proof of some of the other ones because they were afraid of getting laughed off. So yeah, but really, really interesting story. These pictures I love because these are the excited gases, right? So about the only thing that noble gases do that's pretty cute is when you run electricity through them, they glow, right? That's where we get neon lights from. Any questions in the chat? Sorry, I'm not paying attention. Yes, Rayleigh scattering is because of all of the work that Rayleigh was doing on oxygen and light. Oxygen and nitrogen are really good at scattering light of the wavelength that is the color blue. So carbon dioxide, I could literally, you guys, I could give an entire lecture just about carbon dioxide. There's so much to say about this. So carbon with two oxygens on either side, double bonded to its oxygens. It's more or less stable. It's got some reactivity to it. Definitely more than nitrogen, but a little bit less than oxygen. It's what makes beer and soda pops fizzy. So those are the bubbles in your soda pop and your beer, which is probably one of the reasons why I love it so much. It's a big product of combustion. So a lot of what happened on our planet in the early years of our planet was a lot of combustion related stuff, a lot of burning. So that's why we had so much carbon dioxide. And it is a respiration product. So carbon dioxide was originally discovered by Joseph Black. Yeah, and the story of this discovery is pretty cool. So he would take calcium carbonate, which is basically Tums, right? It's the same thing that's in shells. And he would react it and distill carbon dioxide gas from it, and then was able to extinguish, literally pour this gas onto a candle and make it go out. So that was how they figured out that this was a gas that was more dense than air.
Is that what they would use for like fire extinguishers?
Carbon dioxide?
Yeah.
Yeah, absolutely. So that's one type of fire retardant. So there's, sorry?
A suppressant? Or?
Yeah, there's different kinds. So there's different grades of fire extinguishers. I'm not an expert on that per se, but there's different kinds of fires, and depending on what kind of fire you have, there are different types of extinguishers to use. So, so this gets us to combustion, right? So talking about carbon dioxide leads us to the idea of combustion. So I'm sure you guys have heard this term before. It's the fancy chemistry term for burning stuff. So a couple of the reactions that you may be familiar with, but you haven't seen the reactions for: propane and butane combustion. So these are both gases, or butane's a liquid, that when they burn with oxygen, they create carbon dioxide and water, right? So a lot of the carbon dioxide that's in our atmosphere is from burning stuff. So octane, aka gasoline, every time we burn 2 molecules of octane, we make 16 molecules of carbon dioxide, right? So keep that in mind for later. So incomplete combustion, so this is one of the big ways that we have changed the atmosphere forever, right? Since the early 1900s, the Industrial Revolution, we have been burning stuff like it is going out of style, right? Combustion and incomplete combustion have really changed our air. So incomplete combustion is something that we're all familiar with, but we don't talk about very much in chemistry. Incomplete combustion makes products like carbon monoxide. You guys know that monitor in your house that you have to change the batteries for occasionally. Carbon dioxide, sulfur dioxides, nitrogen oxides, volatile organic compounds, and other hydrocarbons. So, and then particulate matter. So particulate matter, when you see smoke from a fire, that's mostly this, right? So just for a little bit of scale, particulate matter, PM, 2.5 and 10. The 2.5 and 10 refer to the size of the particles. So PM 10 is about 10 microns or less. And just for scale, a human hair is about 50 to 70 microns in diameter. So this is about 5 times smaller than that, right? PM 2.5 is 2.5 microns or less. So why do we care about this kind of pollution? Because when we inhale PM 2.5s or PM 10s, those molecules, especially the smaller ones, are often able to irritate our lungs. They cause a constant level of inflammation that can be really unhelpful to people who live in an area where there's lots of this pollution. And the PM 10 is not able to get into our bloodstream like the 2.5 is able to get into our bloodstream in some cases, but does a lot of damage irritation-wise as well. So this is one of the reasons why we monitor this. We monitor the pollution associated with incomplete combustion in various ways. So the ways that we make this stuff: cars, power plants, livestock production, natural sources. There's a lot of natural sources as well, so it's not all us. Biomass burning, volcanoes. The big ones that cars produce are nitrogen oxides, so NOxes, NOx, which is a shorthand for any of the nitrogen and oxygen combinations that can be made. Now we're getting into the catalytic converter. So a catalytic converter is designed to help reduce the nitrogen oxides that are coming out of our car as a result of that combustion, right? So we're burning the fossil fuels. There's always going to be a little bit of incomplete combustion, so we get these side products, but we want to try and minimize those side products, and one of the ways that we do that is with a catalytic converter. One of the biggest pollutants that's hazardous to human health is ozone, and ozone is one of the things that's produced in combustion directly, but it's also one of the things that happens when these nitrogen oxides are out in the air in the world. So the nitrogen oxides, for example, nitrogen dioxide, is what we call a free radical, right? A free radical has an unpaired electron. So you guys remember at the beginning when we were talking about the Lewis dot structures, we had the little pairs of electrons. Electrons like to come in pairs. They do not like to be unpaired, right? So a free radical, a lone electron, is about the angriest thing that you have in nature. That's going to react immediately with anything that it comes into contact with. And the thing that it most often comes in contact with is oxygen in the air. So then it forms nitrogen oxides and ozone, excuse me, which is O3, right? So this nitrogen oxide, you can see, also has an unpaired electron, right? So this will go on to propagate more reactions, right? So free radical reactions are what we call cascade reactions. They just keep going and going and going until you have two radicals that come in contact with each other and form a terminal reaction. How am I doing on time? Okay, cool. Good. So those terminal reactions are pretty unlikely, especially in the atmosphere, right? Molecules are not coming into contact too very often, especially to free radicals, which don't exist for very long. So ozone is readily formed from those nitrogen oxides. Another thing that's able to react negatively in the air that we produce mostly through burning coal to make power is sulfur dioxides. So sulfur dioxides are not as much a product of driving and cars, transportation. They're more a product of industrial processes. So chemical manufacturing, petroleum refining, oil and gas production, storage and transfer, mining, and then again, a lot of coal fire burning. So, okay. So, when you guys hear sulfur dioxide, yes, so sulfur dioxide has a role in acid rain. So sulfur dioxides, when they react with water, form an acid, and that acid is what led to acid rain. How many of you guys are old enough to remember acid rain? Yeah. So the younger people in the audience are probably not aware of what acid rain is because we have all but pretty much gotten rid of this, at least in this country, right? So this is one of the big success stories in terms of regulation. So we talk a lot about the sad face stories in how humans are wrecking the world. And so I like to give a little bit of the happier side of things, right? There's a lot of things that we have done, especially in this country, that have led the way to cleaner air for everybody in the rest of the world. So we have this beautiful agency called the EPA. Their charge is to regulate our air, right? Our air, our water, anything that is out in the world that we come in contact with is regulated by the EPA. So when I was originally researching this, I kind of assumed that some of the other countries that are industrializing currently don't have a comparable agency. And I was very wrong about that. So that's why this is in big pink, because I was very surprised to find out that they actually do have their own regulation, but they don't have any money, they're not funded. And so even though they exist, they're basically like puppet organizations, right? So I don't know if you guys have seen some of the pictures of China's air. You guys remember the Olympics a few years back? Yeah?
Vaguely.
Vaguely, yeah, same. But the air in China is notoriously bad in a lot of places. Like as bad as smoking a pack of cigarettes or more a day. It's founded under President Nixon, a Republican. Yes, this didn't used to be a divisive issue. Unfortunately, it is now. But this is why funding is so crucial to this work. So this is my little PSA for getting out and voting, right? Is that what you vote, who you vote for, absolutely matters in terms of your day-to-day ability to be healthy, right? The EPA under the Trump administration was gutted to a large extent, right? And the damage that was done because of that is something that we probably won't fully realize for years to come, right? And that's not unique to that administration. That was just a particularly egregious example of it, right? But yeah, so you matter, right? These agencies only exist when they're supported by the people that understand how they work. Oh, this was another fun fact. So a lot of the things that the Trump administration did to undermine the EPA actually didn't lead to some of the quality reductions that were expected, mainly because companies now are incentivized by public opinion of climate change as an issue to not do those things. So I thought that was interesting as well. So the progress wasn't, the impeding of progress wasn't as bad as it could have been. But this is a beautiful success story, right? So it's not super sexy, but what this graph is telling you, so the red line here, sorry, that's this red line, is lead, right? So you guys notice that we only started measuring this like a decade or so ago, right? But why is that drop so dramatic? Where was lead coming into our atmosphere? You guys ever go to the gas station and you get unleaded gas, right? There's a reason why it's unleaded. Yeah, exactly. So lead was added to gasoline at one point. I knew the reason, but I forget off the top of my head why. There was a good reason for it though. But we started to see really negative health effects, especially in children or unborn children. So once this became regulated and we stopped doing that, got unleaded gasoline, right? This came down really nicely, right? That's one of the biggest success stories. It is also something that we did, right? So it's not great in that respect, but it's definitely getting better. We've got carbon monoxide. We've got our PM 2.5, our nitrogen dioxides coming down here. And one of the big ones that I wanted to show you is this big blue line here. So starting out way up there in the 1990s and coming way down here, right? That's our sulfur dioxides, right? So this is what regulation can do, right? It can take a problem that was everywhere when I was growing up and make it so that our generation now doesn't even know about it in a lot of cases. First moved to California in 1983. There's still, yes, yeah, it was shockingly not that long ago. I think, is anybody surprised by the fact that there was lead in gasoline? I was like blown away. Even though I see it on the gas pump every time I go there. I'm like, it says unleaded on it. It must have had lead in it at some point. But yeah, so wild ride. So another big success story was the nitrogen oxides, right? So one of the big things that changed in our nitrogen oxides was catalytic converters, right? So catalytic converters, as somebody mentioned in the chat earlier, are something that began being produced in cars and regulated to be in cars, I think around the early 1990s, maybe the late 1980s. I could be wrong on that. But cars that were produced before a certain year don't have catalytic converters and are not required to get them. Now we have to do this thing called the smog test, right? Which is very annoying and costly. But we go in and they test our emissions, right? So they're basically testing, is our catalytic converter functioning the way that it's meant to? Which is to take carbon monoxide, nitrogen oxides, and other hydrocarbons and turn them into water, nitrogen, and carbon dioxide through catalysis that involves mostly platinum, right? So very expensive hunks of metal, but they do a really important job. As a fun side note, this catalytic converter cannot do its job unless your car is warmed up properly. So we don't live in a very cold place, but take that extra couple of minutes in the morning to let your car warm up, because that's how your catalytic converter starts to work. So air quality. The other big one that we have done great work on is ground level ozone, right? So we said ozone is a major pollutant. Some of you were alive at a time when there were literally, there was so much ozone in LA and other places that it was literally toxic to walk outside, right? It was hazardous to be outside. There are still places in the world where that's the case, but thankfully, most of them are not in this country, right? There are still days where we have high ozone levels, and some of that's natural, some of that's naturally occurring, but for the most part, the regulations that we've put in place, like catalytic converters, have done a huge job with reducing the amount of surface level ozone. So, big success story there. Let's see, where am I at the time? So these are some of the other ways that we see these things formed. So we're talking a lot about the pollution, but there's a lot of things that are created naturally through either photochemical, photo meaning light, photochemical reactions, or that are produced by plants, which then are also photosensitive. So volatile organic compounds, VOCs, are formed by plants. And these are something that often will lead to NOxes. NOxes, by the way, coincidentally, are the things that make beautiful sunsets. So if you guys ever walk outside on a wonderful, beautiful night in San Diego and you see the sunset and it's just gorgeous, a lot of that has to do with nitrogen oxide pollution. Sorry. But that being said, we see these beautiful sunsets in remote areas as well. And that's because of this chemistry that happens in nature, right? So it's not all us, right? Some of it is nature itself. So we've been talking about ozone like it's the bad guy, right? But ozone has two very important functions, right? So at the surface level, ozone is a bad guy, right? But up in the stratosphere, that ozone, what we call the ozone layer, is super important. So this beautiful orange thing up here is the sun, and that's light coming down from the sun. So you guys have probably heard of UV, ultraviolet light, yeah? So when you put on sunscreen, right, you're putting on UVA and UVB protectant. So both of these are the lower energy of the bunch. This one is the higher energy, right? So if we come in contact with these, what happens?
Sunburn.
Sunburn, exactly. Our skin literally burns when we come into contact with these, which is why we use sunscreen. If we come into contact with this, which is higher energy, we can have damage to our cells, right? So we can have cancer develop, right? Much more readily with UVC. And the reason why we don't have to worry about that very much is because of this beautiful layer of ozone up in the stratosphere. So the stratosphere, unlike ground level, tends to have things that are able to have a longer lifetime, right? So things that are reactive, that are moving around and doing lots of chemistry, tend to stay in the troposphere, right? Whereas things that are less reactive tend to be up top here, right? So ozone is able to react in that photo reaction with UVC light and essentially absorb it and then translate it into more oxygen molecules, right? So it is super important in terms of human health and preventing cancer. And we were actively participating in the destruction of this stratospheric ozone. Oh yes, so UVA, UVB, or UVA is the longest wavelength. UVB is a little bit longer, and that is a little bit shorter, excuse me. And then UVC is the shortest or the angriest of the bunch. So referred to as ionizing energy. So have you guys heard of CFCs? So CFCs were a commonly used refrigerant for a very long time, chlorofluorocarbons. And they were a perfect refrigerant. So the way that refrigeration works is you take a gas and you heat it up, and then that cools things down, which sounds super counterintuitive, but that's how they work. So this gas was one of the gases that was used in refrigeration. But what would happen is after the refrigerator stopped working, you had all of these refrigeration apparatuses that were left in landfills. And so the chlorofluorocarbons that were left in there were escaping into the atmosphere. And they're so non-reactive that they were able to make it all the way to the stratosphere, right? Where most things are able to react along the way. Chlorofluorocarbons got all the way up into that upper layer of the atmosphere and then happened to react with ozone. So slowly but surely, these chlorofluorocarbons built up in the stratosphere were reacting away all of this ozone and created ozone holes, right? Anybody old enough to remember the ozone holes? I know you are. So this is another one of those issues that we have largely dealt with, right? We will still be dealing with the ramifications of what was done for a very long time because the lifespan of chlorofluorocarbons is hundreds of years. So, so we'll still be dealing with it for a while, but at the very least we have stopped using these compounds. We've changed out some of the atoms that are involved. And so we are doing less to take away that little blanket of ozone that protects our skin when we go outside. So the guy that figured this out is Mario Molina. This is one of my personal chemistry heroes. First Mexican-born to win the Nobel Prize. His research on CFCs and the fact that they react with ozone in the upper layer of the stratosphere was transformational, right? Without this work, we wouldn't have known that this was going on, and he actively campaigned for most of his life, most of his career, for reducing the use of chlorofluorocarbons, figuring out new ways to make better refrigerants that weren't damaging the environment, and also was a powerful voice in climate change talks. So Mario Molina is one of my guys. All right, I'm gonna leave it there because the rest of my slides, and there are a lot of them, 59, we're at 30 right now, are all about climate change, and I love this topic dearly, but I don't think we have enough time to do it justice. So yeah, that's all I got for you. But if you guys want this presentation, I'd be happy to give you the link. And there's a lot of informative websites that you guys can look to, and videos there as well. Yeah, happy to put that in the chat. So questions? I'm not mad if you guys are sleepy. I know I am.
Oh, I had a question from earlier.
Yeah.
You were talking about combustion reactions.
Yes.
And I was wondering, is respiration therefore considered a combustion reaction since
Yes.
CO2 is a byproduct?
It's so respiration is absolutely your body's slowed down form of combustion. Yeah, absolutely. So respiration, just for for everybody's understanding here. The photosynthesis reaction takes carbon dioxide and water and turns it into glucose, aka sugar, and oxygen. Respiration is exactly the opposite, right? So we're taking our glucose with oxygen that we inhale, and we're forming carbon dioxide and water. So it is absolutely a combustion reaction that happens inside our body. Yeah. Yeah, was everybody able to see the link there? Can we somehow artificially reconstitute the ozone layer? That's a terrific question. It's really hard to have an impact on the stratosphere. Does that make sense? So stratospheric chemistry is particularly challenging because the only stuff that gets up there is stuff that is long-lived. And we know that ozone at ground level is not long-lived, right? It reacts very, very quickly with other things. So, yes?
I looked it up on Google for the lead in the gasoline.
Uh-huh.
The reason was that for an anti-knock agent, which improved the efficiency of vehicles
Yes.
and the performance of the engine. It
Yes.
made the engines more powerful.
Yeah, it kept things from gunking up,
It
I
turned
think.
clunky engines into smoother running engines.
Yeah, beautiful. Thank you for sharing that.
But that lead proved to be toxic.
Yeah, shocker, I know. Lead also used to be used in paint, right? So there was a lot of places that we used these things and we weren't able to know the effects until later. Thankfully, once we figured out what the effects were, we were mindful and tried to right the ship, but that's been true of science in a lot of cases. Those are kind of my favorite stories, actually, of where science went really wrong. Because there's so many beautiful success stories in chemistry and science in general, but yeah, it's a very rocky ride. We tend to only talk about the good stuff and not the bad stuff that's happened. But at one point, we were using radiation on people's thyroids because we thought that would help shrink them, and we gave a whole generation of poor people mostly cancer from radiating their thyroid. And the reasons behind that are a whole nother fascinating story in and of itself. But again, if you want to find out more about this stuff, I highly recommend that you check out Sam Keene. He is an incredibly easy to read, accessible science writer, and he writes all about not just chemistry, but biology, neuroscience, all that kind of stuff. The future of ozone looks good. Yeah, it looks good. It looks better. It definitely looks better. So there are still a lot of technologies that we have started regulating in this country that haven't been regulated in other countries, right? So a lot of the things that we can point to as success stories in the United States are not necessarily success stories in the entire world, right? So as nations are developing, they're hungry for energy, the solutions to air pollution are expensive, and there's not a lot of incentive to do those if people don't know about them, if that makes sense. So if your population is undereducated, then it's easy to have that population not care about those things, especially when they're just trying to feed their families. So the future of ozone is better than it was, but we still got work to do. I would say that's true of all things pollution. Yes. Oh, I'm no longer able to share in the chat, Jesus. I'll put my email in there. If you email me, I can send it over to you. Any other questions?
How do we get the link?
I will put my email up for you guys as well on the board with a marker that I probably have somewhere, and you guys can email me and I'll send it to you. Yeah. Or I can put it with the Zoom link. Yeah, that's fine.
Yeah, and I'll also write the link to the Master STEM Lecture Series schedule on the board before we leave tonight. I posted it in the chat as well. And I'd say within a couple days, I'll put it on the master schedule so you can go back and watch the recording.
How do I get to that part? I mean, because like right now I came in here, it's like, all right, now you're saying links and zooms and stuff like that. Because my professor just told me about this year, and he told our whole class and everything. But
I'll write the link on the whiteboard
Right.
before we
Yeah,
get to
it's a bit.ly.
Yeah.
All right, any other questions? Remember leaded gas and ozone holes, yeah, I know. I only know how old I am now because I teach 18-year-olds. And they constantly reminding me of how old I am. So, not too old, but old enough to remember things that they...
Well, you don't look that old.
What's that?
You don't look that old.
I'm not that old, but I'm still old enough to remember things that they don't remember. So, like, I don't think any of them have ever heard of recycle, reduce, reuse. You know what I'm saying? So yeah. Okay, should I stop recording? Did we stop?
Yeah, let me say a few words at the end to see if I
Okay,
can get
go
my
ahead.
video here. Great, hi everyone. Hopefully you can hear me, Don here. I just wanted to thank everybody for coming tonight, and especially thank Professor Moore for being here and giving us a wonderful talk tonight. So again, I posted the link to the master schedule in the chat, and then for those of us who are here in person, I'll also write that link on the board. So again, thanks everyone for coming,
Here's the link.
and hope you have a wonderful evening.
I don't know if you